Hello and welcome. This lesson is an introduction to polynomial functions. It has been prepared for students who are taking the MHF 4U or the Grade 12 Advanced Functions course. So let's get started. A polynomial function is a function in the form f of x equals a0x to the power of n plus a1x power n minus 1 a2x power n minus 2, and we continue the pattern until we hit the last term, anx to the power of 0. As you see in the equation, three letters are involved, letters a, x, and n. And as always, the letter x represents the independent variable. The letter a represents the coefficient. The coefficient can be any real number. And last but not least, the letter n represents the exponent or the power or the degree of the polynomial function. It's very important to remember that n can only be a whole number, which means numbers such as 0, 1, 2, 3, 4. So no negatives, no fractions, no radicals. If n is a radical or a fraction or a decimal, the function will change its nature, so it won't be called a polynomial function anymore. So the leading coefficient is the coefficient of the highest degree term. In our case, in the equation that we wrote at the beginning, then we're going to say that that would be the value of a0. Now, very often when we describe the behaviors of polynomial functions, we have to use certain features of it. And in this lesson, we'll go over all the terminology that we are going to use in order to describe polynomial functions. So the absolute maximum of a function is the highest value attained for all the values in its domain. Okay, for all the values. And that's because we're talking about the absolute value. Now, the absolute minimum is the lowest value attained by the function for all its values in its domain, because it's absolute minimum, right? So the end behavior of a function very often can give us hints about the shape of the graph. The end behavior of a function describes the trend of the y values as x approaches either infinity or negative infinity. Turning points of a polynomial function give shape to polynomial functions. And turning points occur in two different situations. When the function changes the behavior from increasing to decreasing and vice versa. So when the function changes the behavior from increasing to decreasing, so here it's increasing, then it starts decreasing. Then the function has to go through a turning point or creates or makes a turning point. In this case, from increasing to decreasing, the turning point will actually represent a maximum on the graph. A turning point can also occur, as we mentioned before, when the function changes the behavior from decreasing to increasing. So here is a function that is decreasing, and then it starts to, let me do it here. It's decreasing, and then it starts to increase. So from decreasing to increasing. So when this happens, the function will create a turning point, which in this case will actually represent a minimum point on the graph. Another very important feature we look at when we analyze polynomial functions is even and odd degree functions. The reason why we do this is because even degree functions will behave similarly and odd degree functions will behave similarly within their respective groups. An even degree function is a function with the highest exponent equal to an even number. And an odd degree function is a function with the highest exponent equal to an odd number. Now, in the previous unit, we have mentioned together the terms even symmetry and odd symmetry, and it is very important not to mix them up together. The reason why is because very often a function can be even degree, but it doesn't necessarily have or exhibit even symmetry when it comes to its shape. And the same thing for odd degree functions. So let's illustrate it with an example. So here we have two even degree functions, y equals x squared and y equals x plus 2 squared. Both these functions are even degree. That's because the highest exponent is 2, which is an even number. However, y equals x squared has even symmetry, whereas y equals x plus 2 squared does not have even symmetry. Because remember that symmetry is related to the shape of the graph being symmetrical about the y-axis. So if you fold the graph along the y-axis, y equals x squared will have two sides exact same that overlap. Whereas in this case in here, if we fold the graph along the y-axis, we won't see the same thing happening as in y equals x squared. Now the same thing will occur when we talk about odd degree functions. So y equals x cubed will have odd symmetry, and that's because we have rotational symmetry about the origin right here, whereas y equals, for example, x minus 2 cubed will have odd degree. So this is an odd degree function, but it does not have odd symmetry because it's the shape of the graph is not symmetrical about the origin. Okay, so the next thing we're going to look at is the shape of each polynomial function, and we're going to start from degree 1 and continue up to degree 5. F of x equals x is an odd degree function. And that's because the power of x, the highest power we see here, is 1. We're all familiar with the shape of the graph f of x equals x. It's going to be a straight line, passes through the origin, okay? And it makes a 45-degree angle with the x-axis, okay, right here. Now, when it comes to the range of this function, we're going to say y is any real number. And for the end behavior, we're going to describe this a little bit differently. We're going to say that the function starts in quadrant 3 and ends in quadrant 1. I'm going to write the quadrant numbers in here. 1, 2, 3, and then 4. So we're going to say that the function extends from quadrant 3 to quadrant 1. F of x equals x squared. Now this is an even degree function. And that's because the power of x is an even number. We are familiar with the shape of this graph because we've learned this in grade 10, right? And we're going to say that the range of this function is y any real number, but y has to be bigger than or equal to 0. For this function, we're going to say that it will extend from quadrant 2 to quadrant 1. Remember that the extension is always described starting from the left side of the function to the right side. So we are in quadrant 2, going towards quadrant 1. F of x equals x cubed is an odd degree function. And that's because the power of x is an odd number. The graph of f of x equals x cubed, which we can easily actually double check and see here on Desmos. X to the power of 3. Okay, so here goes the graph. So as you can see in here, it extends from quadrant 3 to quadrant 1. So the graph is somewhat curvy here. Okay, and we're going to say that the values of y will be any real number. Okay, because you can tell that the y values are negative and positive. And we're going to say that the end behavior is that of a function that extends from quadrant 3 to quadrant 1. You probably noticed some patterns that start appearing in here. So first degree, third degree, they extend, right, from the same from one quadrant to another. So from quadrant 3 to quadrant 1. So it's the same end behavior. And the reason why is because of the power, which is odd. Now f of x equals x to the power 4 is an even degree function. That's because the power 4 is a number, even number. And I'm going to graph this together. I'm simply going to change the power here, power 4. Now, as you can see in here, we have sort of a parabolic shape, but is wider at the bottom, and it increases faster on the sides compared to y equals x squared. So let me just enter at y equals x squared as well, so we can tell the difference. So the blue one is y equals x squared. So y equals x to the power 4 increases faster and is wider here at the bottom. Okay, so let's draw the graph of it. So it's thinner and wider at the bottom. I'm exaggerating it a little, obviously. So 1, 2, 3, and then 4. I'm going to say that in this case, y is any real number, but it has to be bigger than or equal to 0. So again, notice how second and fourth degree functions have limitations in their ranges, whereas the odd degree functions are any real number y. Okay, and that's a consistent pattern, as a matter of fact. Now, when it comes to end behaviors, we're going to say that it extends from quadrant 2 to quadrant 1. And now, last but not least, we're going to take a look at y equals x to the power of 5. X to the power of 5. Here is the graph. Very similar to y equals x to the power 3. And I'm going to add x to the power of 3 here as well, just so we can see the differences. And then, so y equals x to the power 3 is the green graph, and x to the power 5 is the red graph. So you can tell that the function is flatter around the origin for the red function, so power of 5. And that's the reason because y equals x to the power 5 increases faster than x to the power of 3. That's because the power is greater. As a result, when the x values are very small, then the y values will increase a lot more slowly. So here goes the graph of x to the power of 5. Okay, and the extension will go from quadrant 3 to quadrant 1. The values of y, any real number. Now, remember that, as we mentioned, for the polynomial functions with similar graphical characteristics will be based on their degree. So even degree functions behave similarly and odd degree functions behave similarly. So same and behaviors, and they have limitations in their domains, in their ranges limited. Sorry, no, domain is any real number for both even and odd degree. So the same thing can be said about the odd degree functions. So they have similar and same end behaviors and same range. So for the range, we're going to say that it is any real number. Okay, so moving on to polynomial functions, we're going to take a look now at some more fun polynomial functions, so more complicated, so to speak. So here we have the equation and the graph of a function. So the equation of this function is y equals x squared plus 4x minus 5, and here is its graph. So the highest degree of x here is 2. So we're going to say that the degree is 2, which makes this an even degree function. And the leading coefficient in here is positive. The end behavior goes from quadrant 2 to quadrant 1. So we're going to say that as x approaches negative infinity, the y values will approach positive infinity. So the way we look at it is this. So as x approaches negative infinity, so as x becomes smaller and smaller, the y values increase. They become bigger and bigger. So y approaches infinity. Similar to this on the other side, as x approaches positive infinity, the y values are approaching infinity as well. So y approaches infinity. There is one turning point on this graph. And I'm going to use the term or the acronym TP for turning points. So the next equation is y equals x minus 1 times x plus 2 times 2x minus 1. So remember, since we're multiplying 3 factors, where x is present in each factor and to the power of 1, then the power of this function will be 3, or the degree of this function will be 3. So that's obviously an odd degree function. The leading coefficient is 2, because remember, the leading coefficient is obtained by multiplying the leading coefficient of each factor. So that's a positive number. As x approaches negative infinity, the y values are going down because all the y values where x becomes smaller and smaller are trending down. So we'll say that y approaches negative infinity. And as x approaches positive infinity, the y values increase to infinity. In this case, we will see two turning points, one here and one here. Okay, so with this being a maximum and this one being a minimum point. In the next function, we have y equals negative x cubed plus 2x. We're going to say that this is a third degree function because the highest power we see here is 3, which is an odd number. And the leading coefficient this time is negative. As x approaches negative infinity, the y values are increasing. So we're going to say y approaches infinity. And as x approaches positive infinity, this way, the y values are going towards negative infinity. The function will extend from quadrant 2 to quadrant 4, and the function will have two turning points. Okay. In the next example, we have a fourth degree function, an even degree. Here is your fourth degree. Leading coefficient is 3, so is positive. As x approaches infinity, the y values are all going towards infinity. As x approaches positive infinity, the y values are approaching positive infinity. And in this case, when it comes to turning points, we're going to say we have 3 turning points. Okay, and I want to talk a little bit about these turning points. So here they are. Let me make this a little bigger. So we have 1 turning point, 2, 3, and I'll mark them. So when the function goes from decreasing to increasing, then we'll have a turning point. This is a minimum. This one here, from increasing to decreasing, produces a turning point, which is a maximum. And then we have another, or the last turning point, which is again a minimum because the function goes from decreasing to increasing. See that we have a maximum, a minimum, so 2 minimums. Now, one minimum is lower than the other, and it marks the lowest point on the graph. So we're going to say that this is not just any minimum, but is the absolute minimum. Now, the other minimum point is a local minimum. We call it local because it's a minimum point, but it's minimum for a certain area, so for a certain part of the domain, but not for the whole domain. Now, this maximum in here will be called a local maximum. The reason why is because this function increases to infinity, so the absolute maximum is undefined. Okay, so I hope this made sense, because it is one very important concept and thing to understand when it comes to polynomial functions. Now, the next function has negative x multiplied by x minus 1, x plus 2, x minus 2. So we have x being multiplied 4 times, so that leads us to think that that's degree 4, because x times x times x times x will be, or will give an x to the power 4. The leading coefficient is a negative 1 times 1 times 1 times 1. So the leading coefficient will be negative. And obviously the power or the degree is even. Now let's take a look at the end behavior. As x approaches negative infinity, so this way the values of y will go towards negative infinity. So y approaches negative infinity. As x approaches positive infinity, so the values of y will approach negative infinity. So y approaches negative infinity. When it comes to turning points, we're going to say that we can mark 1, 2, 3 turning points. So a fourth degree function, 3 turning points. Now, this turning point here will mark a maximum. This is a minimum, and this one here is a maximum again. As you see, we have 2 maximum points, but one of them will be the absolute maximum. So the one that marks the highest point on the graph, whereas the other one will be called the local maximum. Now for the minimum here is also a local minimum, and that's because the function continues to decrease to negative infinity. So the minimum, or the absolute minimum, is undefined. So turning points, we have 3 of them. So degree 4, 3 turning points, okay, consistently. So now let's take a look at degree 5 functions. So we have x, x minus 1, x plus 2, 2x minus 1, x plus 1. 1, 2, 3, 4, 5 times x is multiplying itself. Sorry about that. So degree 5, which is an odd degree function. So the leading coefficient, x has coefficient 1 times 1 times 1 times 2 times 1. So the leading coefficient is positive. Now, let's take a look at the end behavior. As x approaches negative infinity, the y values are going down, further down, negative infinity. So y approaches negative infinity. As x approaches positive infinity, the y values approach positive infinity. So as you see here in all degree functions, the y values will go from quadrant 3 to quadrant 1. So they go in opposite quadrants. When it comes to even functions, here is a positive or negative, the y values will go in the same directions on both arms of the graph. So positive infinity or negative infinity. Now let's take a look at the turning points. So we have 1 turning point here, 2, 3, 4 turning points. So a 5th degree function has 4 turning points so far here. And we're going to say this is a maximum point, and this is a minimum point, this is a maximum, and this one here is a minimum. Now, when it comes to identifying them as absolute or local, then we're going to say that this maximum in here is a local maximum, and that's because the function continues to increase to infinity. So the maximum, the absolute maximum, is undefined. So you will call this a local max. Same thing for this point here is a local min, because the function continues to decrease to negative infinity. A local maximum again, a local minimum here. And the number of turning points we're going to say is 1, 2, 3, 4 turning points. So degree 5, 4 turning points. So you probably noticed some patterns in here already. Now, and the pattern I would say here is degree 5, 4 turning points, degree 4, 3 turning points, degree 4, 3 turning points. So degree 2, 1 turning point, 3, 2 turning points, 3, 2 turning points. So there is a relationship actually between the degree of a function, a polynomial function, and the number of turning points. So the number of turning points will be 1 less than the degree of the function. So equation of the graph, 0.5x, x minus 1, x plus 2, 2x minus, so we have 1, 2, 3, 4, 5 factors multiplied. So that makes this a fifth degree function, which is odd degree. When it comes to leading coefficient, we look at each coefficient for every x in each factor. So negative, positive, 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 positive. So the leading coefficient will be a negative number. As x approaches negative infinity, the y values go towards positive infinity. As x approaches positive infinity, the y values go towards negative infinity. So notice how the y values in odd degree functions go in opposite directions. That's because they always extend across, okay? So they either extend this way or this way. So either this way or this way. Now, how many turning points are here? So let's mark them. 1, 2, 3, 4. So 4 turning points. 4 turning points for a fifth degree function. Okay, so 1 less than the degree. That's the maximum number of turning points. Now, let's mark them what kind of turning points they are. So we're going to say this is minimum. This is a max. It's the top of the hill. This is a valley here, so that's a min. This is the top of the hill. And they're all going to be local because the absolute minimum is undefined and the absolute maximum is also undefined because it increases to infinity. Now, very often, now that we know all these features, we'll be able to describe the behavior of functions just by looking at their equations. So what we want to do is describe the end behavior of the function. Now, for the end behavior of the function, we're going to say refer to the degree and the leading coefficient. So the degree of this function is 5, which makes this an odd degree function. That means that the end behavior will be an extension across the quadrants. The leading coefficient is negative. So in this case, we're going to say that the function's end behavior will be the same as actually a linear function, which is the simplest odd degree function with a leading coefficient negative or a negative slope. So the behavior will go from quadrant 2 to quadrant 4. So as x approaches infinity, y will approach negative infinity, and as x approaches negative infinity, y will approach positive infinity. Okay? The next thing is the number of turning points. Now, the maximum number of turning points will depend on the degree. So, degree 5 suggests that maximum number of turning points is 1 less than the degree, so 4. The next thing that we need to look at is the possible number of zeros, and a fifth degree function can be described or can be written as a factor or as a product of 5 factors. So 5 factors means 5 intercepts or turning points. So same as the 5x intercept, same as degree. And if you want to graph this function, then we're going to say that the shape of it would look similar to this. This is just an idea. So it will extend from x approaches infinity, so from quadrant 2 to quadrant 4. So with 5x intercept, so 1, 2, 3, 4, 5. And here we go, 1, 2, 3, 4, 5. So the number of turning points can be 1, 2, 3, 4 turning points. Okay? In a similar way, we can discuss the shape of gx equals 2x4 plus x squared plus 2. Okay? Now, in the next example, we're asked to find what could the graph of polynomial function that with a range y less than or equal to 10 and 3 turning points look like, and what can you conclude about the equation. So if you have a function where y is less than or equal to 10, so 10 will be the highest value, and if it has 3 turning points, then I'll give a turning point to 10, and it has 3 turning points, so that's the second turning point, and here is the third one. One, 2, 3 turning points. So this is a function with 3 turning points. The y values are all below 10 or equal to 10. So this will be an even degree function. And based on the shape I drew, it looks like it's going to be a 4th degree function with 3 turning points. So this was today's lesson about exploring polynomial functions. And I hope this all made sense. I know it's a lot of information to take in, but we'll take things one at a time. So we'll talk more about the examples in class.